So let's do our first example of an integral which has a vector field and dot product dr. Okay, so this problem asks you to do this integration using the following function. The vector field f equals a vector 1 and 1 plus x, and the curve L is anticlockwise circle with radius r, centered at the origin. Okay, so those are the data given by the question. So first step will be to parameterize the curve. So how do you parameterize this curve? So this is a circle centered in the origin. So this curve looks like this. And it has a radius r. So the way you parameterize this is, of course, you could use polar coordinates and use phi as your parameter while you keep rho fixed equal to r. So use polar coordinates, and polar coordinates are written like this. Which you can look up, as always, in the list of equations by looking at cylindrical coordinates, and substituting z equals 0. So to describe a circle, you can fix the radius rho equal to r and use phi as your parameter. Okay, so doing those substitutions, you arrive at your parameterized curve, which is a function of phi, where phi is the parameter, which is equal to r cosine phi and r sine phi. And what are the limits for phi? Our parameter goes between 0 and 2 pi, right? Excellent. So that's the step 1. Step 2 is to find the vector dr, the differential displacement dr. And we know different ways of doing it. So the first way, maybe we can do it by direct calculation. So if you do it by direct calculation, you have the equation that dr is equal to the derivative of r with respect to the parameter phi times d phi. So let's calculate the derivative of r with respect to phi. So here we have r with respect to phi. So we do the derivative of that, and we get minus r sine theta and r cosine theta. So that's the derivative of r phi with respect to phi, which I have substituted here. And then we multiply times d phi, don't forget about that. So that's our differential dr, which we can write, if you want, as r times minus sine phi cosine phi d phi. Okay, another way we could do it is by intuition, geometrical intuition. So by thinking about a certain angle phi and increasing the angle by an amount d phi, so then the length of this arc dl is simply equal to r d phi. But dr is a vector, so we need to find the dr vector. And remember that dr is equal to, it has the length of dl, but then it has a unit vector in the direction tangent to the curve. So in which direction, what is the direction tangent to the curve for a circle? So when you are doing a circle, so of course the direction tangent to the circle is just the unit vector e phi, right? So the unit vector e phi is the unit vector tangent to the circle, which means that we can figure out that dr is simply r d phi as the length and in the direction e phi. So now my question would be, is this equal to this? Yes, they are just different ways of writing it, because e phi hat, if you go to our table unit vectors, e phi hat is minus sine phi x hat plus cosine phi y hat, which is exactly this vector here. Okay, so these two methods agree perfectly. Finally, a third way of doing it is to look it up on a table. And the way to look it up is we would look into polar coordinates, and then I would substitute the fact that d rho equals 0 because we are not changing our radius, and also d z equals 0 if we are in cylindrical coordinates, which is the same thing. Yeah. So polar coordinates is the same thing as cylindrical coordinates when z equals 0. So then we use cylindrical coordinates and we substitute that we don't change the radius, we don't change the z value, we only change our angle phi. So we go into the table, we look into cylindrical coordinates, but not this table. This only says the coordinates and the unit vectors. We want here, differential displacement. Okay, so cylindrical coordinates, differential displacement, dz goes to 0, d rho goes to 0, and we are only left with this, which is rho d phi e phi hat. Okay? Perfect. So the three methods agree. Excellent. Third step, evaluate the integrand at the curve. And now is where things will get different from what we were doing with the other types of integrals. Because we will need to do a dot product, yeah? So what is the integrand? The integrand is f dot dr, where f is this function here, and dr is this function here. So we need to do f dot dr. And not only that, but we need to evaluate f at the curve. So we can write it as r of phi. So we need to substitute the x, y, and z values that appear in the curve into f. Okay, so let's see what I mean by this. So f dot dr is this function f, which is 1 and 1 plus x. Okay, dot dr, which is r minus sine phi cosine phi d phi. Okay, so clearly here we have two vectors of the same size, so we need to do the dot product. But also we have an x, and we have to substitute. We cannot have x's in the integrand because x is changing as we move around the curve. Okay, that's like kind of the rule. Anything that changes as we move around the curve, you need to write it as a function of the parameter phi. Okay, which means that we need to substitute x equals r cosine phi, which is the equation of the curve. Okay, so when you are moving around the curve, the x value is always r cosine phi. So we need to substitute that into x. Let me write it here. From the curve, we know that x equals r cosine phi. If the function f had y's in it, we would have to substitute y equals r cosine, sorry, y equals r sine phi. Yeah? Okay. So we substitute that and we get 1 plus r cosine phi dot r minus sine phi cosine phi d phi. So developing this dot product, we end up with r multiplying the following: cosine of phi plus r cosine squared of phi minus sine of phi times d phi. Okay, and now as a sanity check at the end of step 3, you know that everything must be a function of the parameter only plus constants. And indeed here we have phi, we have the parameter, and we have r, which is a constant. Okay, so everything is so far is fine. So now we are ready to calculate the integral. So this is great because now our integral f.dr, we have managed to write this integrand as a function of phi d phi. So then it becomes a simple integral of phi. This is a simple integral of phi between 0 and 2 pi. Integrating cosine of phi is very easy. Integrating sine of phi is very easy. The only slightly tricky part would be integrating cosine squared, and I'm going to use the trick that cosine squared is equal to 1/2 plus 1/2 cosine of 2 phi. I use this identity, yeah. So then doing this integral is fairly easy. We can keep the r outside because it's a constant, multiplying everything. So it's r times, let's do the integral. What's the integral of the cosine of phi? So the integral of cosine is the sine. Okay, what's the integral of 1/2 r? It's equal to r phi over 2. Then what's the integral of 1/2 r cosine 2 phi? That will be r fourths sine 2 phi. Right? You have to think backwards. When you do the derivative of this 2 will come out, so this will become r over 2 times the cosine of 2 phi. Yeah? Okay, and finally the integral of minus sine is the cosine of phi. Okay, so that's how you do this integral. Evaluate it between 0 and 2 pi. So if you evaluate sine of 2 pi is 0, this will be 2 pi divided by 2 times r. Sine of 4 pi is 0, and cosine of 2 pi is 1. And then when you subtract with the 0, sine of 0 is 0, sine of 0 is 0, cosine of 0 is 1, and this will be 0. So if you do the additions, you end up with pi r squared. Okay, excellent. So that completes our first example of an integral of this kind. Excellent. Thanks for watching. See you in the next video.